Okay, hello, good afternoon, everybody from Hellenic Mediterranean University. We have another Sci Cafe Colloquia talk for our ecosystem and for our university in Athena European University. It's a great pleasure and honor for us to have today with us Professor Humberto Michinel, if I'm pronouncing correctly his name, who is currently a professor at University of Vigo in Spain. And Professor Michinel studied in Madrid, University of Madrid and Santiago de Compostela for his doctoral and postdoctoral studies in the field of nonlinear optics. So Professor Humbert, today he will speak to us about his fascinating topics of optical vortices in highly non-linear optical materials. So please, Professor, share your screen and start your presentation. Your presentation should last approximately 40 minutes, followed by 10 to 15 minutes of a Q&A session. Thank you very much.
Thank you for the nice introduction. I assume that you can hear me and you can
Yes, we can hear you. We can see your screen in a full screen mode. So excellent.
I will start the alarm just to so I will talk about a topic which is maybe a little bit technical. So if you are not really familiar with quantum optics or singular optics or nonlinear optics, I will try to avoid unnecessary technical details. I assume that most of the people will be familiar at least with optics or with lasers. But even if not, I will try to bring some images from other fields in physics, which could help to understand a bit better the talk. So what I will be trying to explain is that light that has been always considered as a gas of photons since Einstein proposals in the beginning of the 20th century. If light is a gas of photons and gases can be turned into liquids, so maybe light can be turned into a liquid. This kind of liquid, if we use laser light, coherent, pure coherent light to make this liquid, of course, this liquid will be a superfluid. And the properties of superfluids will appear in a natural way in this kind of surprising liquids. So I will try to explain it by bringing some examples. So you are, I think that you may be looking at this video on the left side of the presentation, and this is probably the main topic of my talk. So I hope that after my talk you will be able to understand what this is, the meaning of this video, and how this video can be represented numerically and in experiments. So first, well, let me just briefly introduce the summary of the talk. So I will explain some properties of vortices and optical vortices. Then I will focus on optical vortex. Okay, this is a typo there. It's optical vortex solitons, not bolitons. Then I will introduce the liquids of light. And then I think I can admit some people here because there is, okay.
No, I will take care of this process. Don't worry.
Okay. Then I will introduce the concept of vortex lattices and vortex crystals, and finally I will talk briefly about the forces between vortices in this superfluid. So first of all, let me introduce my institute. It's the Institute of Physics and Aerospace Sciences. It's at the University of Vigo at the campus in Orense in Spain. So there is a photo of the institute. You can see on this website, if cae.uvigo.es, more information about it and many things that we do, not only in physics, but also in aerospace, science, and technology. So, vortices are present in usual liquids. So you can see, for instance, how you can produce in a swimming pool vortices with this nice experiment. So vortices can appear isolated, or they can appear in pairs, or even in more complicated structures. In a swimming pool, you can see that they can be seen very easily. And you have also not only the two-dimensional version of the vortex, you can have also three-dimensional configurations like those produced by the dolphins. And these structures appear in many fluids, not only liquids. They appear also in gases, of course. And the question is, as I was telling you in the introduction, if we think of light as a gas of photons, so if light is a gas, could vortices be produced inside this gas of photons? So the answer is yes, and the procedure to produce them is quite simple. How can we produce optical vortex? So this kind of rings inside a field of light. So the simplest way of producing them is by using a diffraction grating. Okay, so a diffraction grating is a periodic structure of stripes, and we can shine this periodic structure with a laser. So we have the input laser, and in the observation plane, after the diffraction grating, we will see a periodic pattern of spots of light. Okay, so if instead of a usual diffraction grating, we use this kind of grating, this periodic fringes, but at some point, some of the fringes join at a point, producing this type of fork pattern. So if we use this with a laser beam in the observation plane, we will see a pattern which is the bright spots, but at the center of the spots there will be dark holes. Okay, so these holes are a signature of the presence of an optical vortex inside a laser beam. And associated with these patterns are the so-called, so this is the holographic mask, the concept of topological charge. So what is the topological charge of an optical vortex? Is the number of windings that the phase of light is endowed around the central hole. So you can visualize it like in this video. If you imagine that the phase of the light is swirling around the central hole, just like in the water when we open the flux of the vortex. Okay, so just imagine that in a vortex inside a laser beam, there is a hole, like in the video, and it is the phase around the hole that is turning around it. Okay, and as I told you, it is very easy in a lab to produce these structures, which usually are called topological structures because as you know, topology is characterized by the number of holes in a system. So any system with the same number of holes is topologically equivalent to another system with the same number of holes. Okay, so we can produce vortices inside laser beams with the use of these holographic masks, and the phase, the complex field of the laser has a typical structure which is characterized by integer numbers that are called the topological charges. So what can we do with this optical configuration, with these optical structures? For instance, we can do nice experiments, for instance, merging two vortices, which are illustrated in the left part of the slide. We have two different vortices, one with a topological charge L equal 4, and the other one with topological charge L equal 1. Okay, so this means that the phase in the left vortex is swirling around the central hole 4 times faster than in the second vortex. Okay, so we have two holes embedded in a laser beam and with a different phase structure. So in the lab, we can mix these two beams. We can make them interfere. By interference, we mean that we can add one vortex to the other one. So basically, this means that I will put the small vortex inside the big one, okay, in the center. So the pattern, the interference pattern that appears after we do that in a coherent way, we can observe interference because we have laser light. So laser light is coherent and we can observe interference. So we have two possibilities. If I put +1 vortex inside the big one, I will have, as a result, 5 vortices. And if I put a -1 vortex inside the other one, okay, so now this is an error. This is the case of, okay, this is the -1 case, and the +1 case is this one. Okay, so we see that we can perform algebraic operations with vortices. We can add them, we can subtract them, and the result are vortex lattices or vortex arrays. I would like to remember that the existence of vortex lattices, of periodic arrays of vortices, is always considered as a trace of superfluidity in any system. So if you have, for instance, superfluid helium, and you start to rotate it, first it will appear at some frequency of rotation, it will appear one vortex. But if you increase the frequency of rotation, this vortex will split into 2, 3, 4, 5, n vortex, forming a complex lattice. So this happens because superfluid helium is a superfluid, okay? So the existence of these patterns of vortex lattices is a trace, is an evidence of superfluidity inside a laser beam, inside this coherent gas of photons, okay? So, but I was telling you that I'm more interested in vortices inside a liquid, not inside a gas, because usual light is considered as a gas. So what has this to do with the liquids of light? So the idea of the liquid of light came some years ago when we performed some numerical simulations trying to understand the total reflection of a laser light in the boundary between two different optical materials. So the optical material on the top part is a nonlinear optical material with a very specific refractive index. So the material in the top has a refractive index that initially grows with the intensity, but at higher intensity, it decreases. So this is the technically called a cubic quintic material. So you can imagine that the refractive index, when it grows with intensity, it means that light will go to the parts of where there is more light. It's very similar to a gravitational collapse. So in a gravitational collapse, if you add matter to a system, the matter will concentrate more and more due to the effect of gravity. So this is what happens in nonlinear optical materials, because if you have a refractive index which is higher with the intensity, the light will concentrate in the parts where the intensity is higher. And if we have no mechanism of stopping this, the light beam will undergo collapse, very similar to what happens in black holes or this kind of systems. But if the intensity is very high, in some cases, the refractive index will become in the opposite effect. So it will contrast, it will compensate the collapse. And the question is, what kind of light system will we have in this type of nonlinear optical material? So one simulation that we made long ago was this. We are following the laser beam on the right hand side through its propagation, and we observe that the total internal reflection resembles the behavior of a liquid. So the input beam interacts with the surface of separation. It experiments total internal reflection, but after the reflection, it splits into filaments. And of course, the number of filaments depend on the incidence angle and so. But the question is that this image, this is very powerful if you try to think of light as a liquid. Okay, the problem with these cubic quintic materials is that they don't appear spontaneously in nature. It's not easy to find these materials. So and you can also, of course, observe what happens with a laser beam which has a vortex inside. So the question is how we could prepare this liquid of light. Is it possible to do it in an experiment? Well, it took us some years to understand how we could produce these kind of systems from a physical point of view. And we came with the idea of controlling the refractive index of some material, a gas, for instance, using quantum technologies. And if you're not very familiar with quantum optics, what I could say is that when you have a gas of cold atoms, for instance, rubidium, you can use lasers to change the optical properties of this gas. because with light, you can change the quantum levels inside the atoms, okay? By changing the quantum levels inside the atoms, you can have macroscopic properties of this gas that can change enormously. For instance, you can make a gas totally transparent by using a technique which is called electromagnetically induced transparency. So I don't like this name. I prefer the name quantum invisibility, but it's not very popular. So the technical name is called electromagnetically induced transparency. The idea is that you can tune the atomic levels with a laser beam. So a different laser beam can go through this material with no absorption. So the material will become totally transparent for another laser beam. So when you make a material transparent, you are changing the optical properties, the linear optical properties of the material. So what we studied was, is it possible with these quantum techniques to change not only the linear properties of a material, but also the nonlinear properties of a material, okay? So the idea is, okay, we have a gas of cold atoms inside a vacuum chamber. This is our optical material, our optical system. Can we use lasers to change the refractive index, not only the linear part, but also the nonlinear part, and achieve this kind of exotic nonlinear optical systems? And the answer is yes. So we made the calculations. It's quite technical stuff, horrible formulas, but the idea is that with these quantum techniques, you can obtain not only a change in the linear part and the nonlinear part, but you can make this change giant. By giant, I mean several orders of magnitude that is usual in nature. And you can change this, keeping the transparency of the medium. So you can achieve a transparent material, which is very good because we don't like to be absorbed by the material. We don't like the material to be heated and light to be lost. So you can have a totally transparent material with nonlinear optical properties that are tunable. And the good part is that you can achieve this in the milliwatt regime. So you don't need gigawatt or petawatt lasers to do nonlinear optics. With these techniques, you can do it in the milliwatt regime, okay? So with this, you could produce very interesting profiles of laser beams with these exotic shapes that are plotting here. The question is that this idea was put forward by myself and my colleague Manolo Quiroga in 1996, very long ago, but we did not have that time the ideas of changing the refractive index with lasers. So it had to wait until somebody took the passion to do it. So Wu and co-workers in a really remarkable experiment in 2013 achieved this in their lab in the US. And they produced for the first time this kind of droplets of light. This light condensates with top flats, which can have also vortices inside. So you see the yellow spot in the middle of the big red spot. So the big red spots are light, laser light, and the yellow spot in the middle is a hole, which is the trace of an optical vortex. And these really nice experiments in nonlinear optics are done in the milliwatt regime. So this is the main consequence of this quantum control that you can have with optical systems. So basically, the bottom line is that the liquid of light has been already produced. It appears in this kind of exotic nonlinear optical materials, so we can calculate many things that can appear in this liquid of light. So we made a lot of numerical calculations. So the type of vortices that can appear here, and you can have vortices with giant topological charges. These are the profiles of the laser beams of some of these exotic vortices. So in this case, how these vortex lattices will look when you have a liquid, not a gas. So these experiments we made in the lab were made in the linear regime, where light is a gas, a coherent gas. So of course, it's a superfluid gas. You will have vortex lattices, but how does this look in the liquid of light? Well, we made some nice simulations, and we achieved this kind of results. So in the liquid of light, what you are observing here is a transverse cut of a laser beam, and we are following the laser during its propagation. So what we have here is a droplet of light. These days is very popular, the concept of quantum droplet. So this is a quantum droplet of light with many vortices inside. So what you see is that the vortex structure, when you produce it, it's a set of vortices that rotate in some sense. And the question is, if the vortices here are rotating, but more or less keeping their interdistance constant, will it be possible, for instance, to make them stop? Because if you are able to get these dark spots not moving, you will have something similar to the vortex crystals that have been studied in many fields in physics. So, well, the answer is yes, you can have vortex arrays that remain inside the droplet of light. So these are transverse sections of different laser beams. So if you cut the laser beam from a transverse plane, you could have different types of vortex structures. The amplitude will look like a set of dark holes in the middle of the laser beam. And the important thing here is that these structures, these vortex structures, will not change during the propagation of the laser beam. So, and this is due because of the very specific phase structure that they show, that I'm showing here in the bottom row. So, how is the behavior of these laser beams? Well, we can explain it with a very simple model of forces that I have called topological forces. So this is the idea is that the topological charges of the vortices endow them with some kind of force, so the vortices can interact through these forces. So keep in mind that the outside vortices in all these pictures are single charge vortices, so they have topological charge 1. And these topological charges are opposite to the charge of the central hole. So in the vortex structure in the left-hand side, we have 3 single charge vortices of topological charge +1 in the outside, and a central vortex of topological charge -1 in the middle. Okay, so in the second structure in the center, we'll have single charge vortices in the outside and a vortex of topological charge 2 in the center. And the structure of the in the right side is formed by 7 vortices of charge -1 and a central vortex of charge 5 in the center. So there is, of course, a rule in the construction of these vortex structures. The question is that you can apply the forces of all these vortices to each other if you assume that these forces are proportional just to the charge. So the force between 2 vortices is proportional to the charge of the vortex and inversely proportional to the distance. And with this very simple rule, you can calculate the equilibrium condition. So the equilibrium condition, which is put here, gives you the structures that will not move during propagation. So these are our vortex crystals. Crystals in the sense that the holes are in positions that are kept constant during propagation. So they act like, the atoms inside a crystal, which cannot be separated from their stability points. And we have checked that these crystals are highly stable, and we can see it in this numerical experiment where we have 2 laser beams that will interfere at some point. So if you follow the structure of the beams in the transverse plane, if you are following 2 beams that are approaching each other at some angle, what you will see in the transverse plane is something similar to a collision. So this is what happens when these 2 beams interfere. The first thing is that as these beams are inside in the form of a liquid droplet, they display surface tension properties. So the 2 beams are launched with a global opposite phase. So there is always a notch at the center of the field because you have destructive interference. So the idea is that when you make these 2 beams interfere destructively, the central notch acts as a barrier, so they will not fuse. But there is some energy related with the surface tension of the liquid. So you see that the border of the beam is deformed in a similar fashion as liquids do. And the important question here, because this is well known, we proved this several years ago, but the interesting thing here is that the vortex crystals that are inside the beams, they preserve their shapes. So this means that these vortex crystals are stable even against collisions of the beams. And this is due because the topological interactions between the vortices keep them on their sides. So, we have also observed some very surprising properties of these vortex structures, and I will put a video now. And the interesting thing of this video is that we are just following the propagation of a laser beam. We are always cutting the laser in a transverse plane. So we are following the laser during its propagation. The laser beam is self-trapped. So this means that here we have no waveguide. So it's just the propagation of the laser beam inside this kind of exotic nonlinear material. It is well known that in these nonlinear materials, we have lasers that do not spread, do not diffract. They are, well, solitons in the general sense. So we have these self-trapped beams. This is very well known from the 80s, 90s. And the question is that if we put one vortex crystal inside this laser beam, let's see what happens when we follow the propagation. I repeat that there is no waveguide. So initially, the crystal preserves its shape, but suddenly it rotates and it makes this periodic change in its shape. I repeat that there is no optical waveguide here that prevents the beam from spreading. And well, this is a very, to me, very surprising behavior. I have observed many phenomena in nonlinear optics, but to me, this behavior is quite amazing. So in some sense, this kind of vortex crystals, under some parameters, this does not happen in all the types of beams that we can have here, but some of them show this quasi-stable surprising behavior, which is highly periodic. So let me just comment some future research on this area. We have seen in the first videos when we saw the dolphins and the vortices inside the swimming pool that usually in nature we have three-dimensional fluids, three-dimensional liquids. So, of course, in optics, we can also have this. We can have, instead of a continuous laser beam and a two-dimensional plane perpendicular to the propagation, we can have pulses, light pulses in nonlinear materials. So, light pulse is like a bullet, and this bullet is a three-dimensional object. So, in 3 dimensions, the vortices, I can put the videos in motion. So vortices have a really more complex structure because all these simulations and experiments I've shown you, but that were two-dimensional. So this two-dimensional plane is in fact a perpendicular cut of a three-dimensional, more complex structure. So when we have vortex crystals in 3 dimensions, what we have is something similar to what I'm showing in the left-hand side. So in the horizontal plane, you see the structure of a vortex crystal, but in fact, the vortices correspond to vortex lines that are perpendicular to the plane, to the horizontal plane, and yield a much more complex structure in 3D. The other simulation is the optical analog of the vortices that are produced by these dolphins. So we can have these tubular vortices produced inside the liquid of light or the gas of light, and they will follow propagation and dynamical rules very, very similar to the vortices that are observed in usual fluids. Okay, so there is some future research to be done here, in the sense that we can have more complicated structures in the 3-dimensional world. Of course, from the computational point of view, this is more challenging. But we have codes developed for it, and this is what we are addressing now. All the 3-dimensional properties of this kind of beams. So to conclude, what I would like to highlight is that optical vortices are very interesting topological objects. They are, in some sense, similar to the vortices or whirlpools that are easily observed in rivers or in the swimming pool or whatever. They display a rich variety of interactions due to the fact that they are charged with this topological charge. This can be produced in optics. This is well known since many years ago. In the linear regime, they are similar to the vortices that appear in gases. With lasers, what we have is always a superfluid gas or liquid, because photons are a coherent system. So in a coherent system, all these structures, which are topological objects and they are produced by interference or diffraction, are much easily observed, because in a coherent system we don't have decoherence or noise or white light interference or whatsoever. So the point here is that we have go a bit beyond the usual optical vortices in linear optics, and we have brought this field and mixed it with the idea of the liquid of light. And this idea that we put forward some years ago is now under research in similar fields, like the field of quantum droplets. But what we have here is that in a system of coherent bosons, like photons or like neutral atoms in other fields, when you have this coherent system and you have attractive interactions on one hand and repulsive interactions when the density is very high, you can achieve a phase transition from a gas to a liquid. As you have a totally coherent system, which in fact is at 0 temperature, you will have some kind of quantum phase transition in the sense that it is always interpreted that quantum phase transitions take place at 0 temperature due to quantum fluctuations, but this is a very different type of thing. You will have a phase transition in a system which is at 0 temperature, but which has no quantum fluctuations because your temperature is really equal to 0. So this is a nonlinear phase transition due to the nonlinear interactions inside the fluid taking place in a system, in a classical system, which is at 0 temperature and is non-quantum. So my point here is that there are quantum phase transitions at 0 temperature that are non-quantum driven. And I'm quite sure that this is a new thing. So, and the question is that this optical vortices has also a rich variety of dynamics, and they can be, of course, used for constructing more and more analogies between optics and laser systems and other superfluid systems, which go from superfluid helium to Bose-Einstein condensates or even neutron stars. So if you want to read more about this, I have put there a couple of references. Of course, if somebody is interested on going deep inside this field, you can contact me. And I would like to thank you for your attention. I hope that the time is okay. If you want, I have more slides, so I can put more videos if you want. I think that you are, George, you are muted.
Okay, can you hear me now?
Yes, yes.
Thank you very much for keeping the timing very sharp. So perfect. Thank you very much. And thank you very much for the very interesting and nice presentation about this interesting research topic of nonlinear optics. So now the floor is open for questions. We have at least 5 minutes, so maybe we can have a few questions. So please type them in your chat or raise your virtual hand. So I can see Professor Kaboulakis already, his virtual hand. So please, Professor.
Well, first of all, thanks a lot. Wonderful presentation, I must tell you. And since I've been working on cold atoms for many years now, I really enjoyed these, parallels. So if you ever come to Crete, please contact me. I would love to talk with you, I should say. But let me just ask you a few questions. First of all, in the first view graphs that you showed us, I mean, a photon, does a photon get somehow a rest mass? And also, do you have interactions? Because vortices and superfluidity and all these things rely on massive particles which interact with each other. So I got confused in the first part of your presentation about this.
Yes, well, the idea is, okay, I don't want to go into very, very technical details, but the idea is that, in fact, the nonlinearity is some kind of dressing of the photons, endowing them with some, well, I would not call it mass, but in some sense, photons behave, if you are familiar with Bose-Einstein condensates or cold atoms, the nonlinear Kerr effect is like a two-body interaction, and the highly nonlinear coefficients is a three-body interaction. So this in the language of Bose-Einstein condensates, we will have a system with two and three-body elastic interactions of opposite signs. So it's like the photons inside the nonlinear system behave like if they were atoms with a scattering length which is negative for the two-body interactions and positive for the three body. So when you have two photons, they will try to attract each other. They will self-focus. And when you have three photons, they will experience a repulsion.
Okay. Now, about these materials which consist of rubidium atoms, let's see, these are materials which help us realize experimentally this electromagnetically induced transparency. Did I understand this correctly?
Yes. You can calculate. Well, this is very technical, but the idea is you can make the calculation for this kind of scheme levels. So you have a gas in a 4-level system, like for instance rubidium-87. You can use a coupling beam, a laser beam with some frequency, and another laser beam with another frequency. One laser is the pump beam, and the other laser is the coupling beam. So the pump beam will be pumping atoms from level 1 to level 3, and from level 2 to level 4. And then you will have another laser beam which will couple this atomic structure. So you can calculate the nonlinear susceptibility to high order. Most of the people, when we address this problem, these people coming from atomic physics, they don't like nonlinear optical effects, because nonlinear optical effects will destroy almost everything. So the idea was to, okay, let us calculate the Kerr coefficient, so we are far from self-focusing and things that will destroy our nice atomic physics experiment. But I am from nonlinear optics, so I like nonlinear optical effects. So we calculated what happens beyond the Kerr effect. So if you do the calculation of the full susceptibility, you can have an expression where you will see that it could happen that for low intensities, you will have a self-focusing response, but for higher intensities, you will have a decrease in the nonlinear response. So you will have this 2 and 3 body elastic interactions. And the important thing is that you can keep the system transparent. You will avoid absorption. Okay, it's like in a Bose-Einstein condensate, is that you are avoiding phase resonances that will make your system to have high nonlinear losses. Okay, so the question is that, well, we did not the experiment because we did not have enough money for doing it, but this was due by these guys. So they read our paper and they understood it, what was really surprising for me. And what was really, really surprising is that they were able to do the experiment and they found this light condensate. So this has been experimentally done. And well, this is the usual experimental stuff of people doing electromagnetic induced transparency and slow light and this kind of things, which are, of course, they are very, very close to BEC and atomic and cold atoms experiments. So any lab that is strong in cold atoms can do this.
Okay, thanks a lot. Very nice.
Thank you very much, Professor Kavoulakis, for the question, and Professor Michinel for the answers. So thank you very much for the nice discussion. We have few comments from Lago Poso. Thank you very much, Humberto. It was a pleasure to hear you. And another one from my colleague, Professor Iliodakis. Thank you very much, Professor. Your presentation was quite clear and interesting. Is there any other question from the audience? I have one just out of curiosity, and just to mention, this is not, I'm not a expert in the field of nonlinear optics, but I saw in one of your last slides, you had a slide regarding the a time scale of your systems. But could you please explain me what is the lifetime or the stability of this system?
I think that you mean this slide.
Yes, exactly.
We call it time, but in fact, what you see, this counter, is that you are following the beam through the propagation distance. So you have a continuous beam, and you are following the perpendicular plane through the propagation. So
and for how long it will stay stable, this system?
Yes. The question is that you will have the first thing is that you, in these systems, these exotic systems, these droplets of light, they will not spread due to the surface tension that keeps them without spreading. So you will have non-diffractive beams, okay? If you are familiar with non-diffractive beams in optics, usually non-diffractive beams like Bessel beams are infinite. But here you have a finite beam which does not diffract. So a soliton, a two-dimensional soliton. Okay, this is well known. It was Pierre Cara from Poland in the 76, the first one to realize this, that you, with this balance between self-focusing and self-defocusing, you can have a stable beam that does not diffract. So we are following the beam through its propagation. So this time, in fact, is propagation distance, but it's an adimensional counter. You can follow the beam up to infinity if you want. It will not diffract, never. And the question is that at some parts during the propagation, the structure of the vortex will be rotating suddenly, very suddenly. So they will remain at the side. I can show it again. They will remain quite stable, but suddenly they will rotate. But they will rotate and remain in this position for some distance. And after that, they will rotate again. This is quite surprising behavior to me. But, well, you know, this is the kind of things that you can have in these systems. And of course, the important thing here is that you don't have any kind of waveguide here to keep the beam focused. Okay. It's just light propagating through nonlinear optical material.
Okay, thank you very much. Very interesting, and congratulations on your excellent results.
Yes, I would like to, of course, thank Athena University for this opportunity. And I would like also to thank you guys in Greece for organizing these nice conferences. Well, I
all
hope
the pleasure is ours, and it was a very big pleasure and honor for us to have you in our Friday talk. Thank you very much, and we have to close this session now. Take care, and hope to see you in another Athena talk in another Friday. Bye-bye.
Okay.
Bye.
See you.
Bye.
Bye.